OpenStack's chapter summary, chapter 9, statics and torque. I'm going to start off with a cool toy here that I built myself. Check that out. So this is a Tensegrity. And it looks like it's impossible, but it's clearly not impossible because I'm holding it in my hands. It couldn't be impossible, right? And I'm going to show you how this works. And I actually have a good problem to solve for this that I'll have in another video. But you can build something like this, and we'll talk about that. But let's get straight to the most important point. Equilibrium. Okay, so the chapter says statics and torque, and in statics means equilibrium. In the past, suppose I had an object. Let's say it's this eraser, okay, and I have it in equilibrium. And we're looking down on it, so we're worried about just the plane of the board. So here's my eraser. I can push up with a force of, let's say, 1 y hat Newton, and I'll push down with a force of -1 y hat Newton. Then I could say, let's call that F1, F2. F net is F1 plus F2 equals 0. Now, that's a sum, right? Yeah, one is in the negative y direction, but they're vectors, and we add them as vectors. So that's what it looks like. That's what F net means, net, add, okay? This is what we've done before. We said the net force is equal to 0. And if I wanted to draw this as a free body diagram, I would draw it like this. F1, F2. So I would draw this dot, and I draw all the forces acting on that dot. That's what we've done. But imagine that I have my eraser right here, and I push with the same force, F2, and the same force, F1, 1 and 1. They both have 1 Newton. But now I push right there, and I push right there. It's going to rotate. It's not quite in equilibrium. Okay, so that would look like this. So in this situation, it does matter where on the object the forces are applied. And we're going to need an extra constraint for equilibrium. So we're not just going to have the net forces are going to be equal to 0. We're going to say the net torque about some point is equal to 0. And this deals with what we call rigid objects, or rigid bodies. Because we're going to assume that I can apply my force at different locations, but the object maintains its shape, which isn't always true. But in this case, yes. So we're going to deal with objects that have size. The location of the force matters, but the shape doesn't change. Okay, so let's just jump into it and talk about this new definition called torque. Torque is, I'm going to go ahead and write it, and then I'll show you an example. We use the Greek letter tau, and it's equal to the applied force, the location, this is technically O, the distance from the point of rotation, which you can pick, the reference point O, to where the force is applied, and the sign of theta, where theta is the angle between R and F. It's technically a vector operation, but the book kind of like, you can't handle vectors, we can't handle these complicated vector operations, so we're just going to give it to you like that. So that's fine. In 2 dimensions, this works fine. So imagine that I have a stick like this, and I have some point. The point does not have to be where it rotates about. You can pick whatever point you want. Okay, so that's your choice. It's sort of like the origin in the free body diagram, and which direction are the x and y axis. It doesn't matter. But I'm going to pick that as my point O, and now I'm going to apply a force like this, F, and this is, I'm going to draw that as a vector. And then I'm going to write the vector R, which is from that point to where the force is applied. And then I have this angle theta. So the torque would be R, F, sine theta. So we're going to write it as a scalar value. Like I said, technically it's a vector. Now, we're going to use the convention torque equals positive is, let's see, a positive torque would be counterclockwise. A torque is negative would be clockwise. Okay, so if this wants to make it rotate that way, that would be a negative torque because that's clockwise. If it wanted to make it rotate this way, that'd be a positive torque. And again, that's a convention. It comes from what we call the right-hand rule that you'll look at in the second semester in more detail. Okay, so just a quick demonstration of this. I don't have my door. My door is right here, but I'm not going to use it. So suppose I have a door like that. These are walls. And this is the hinge of the door. And this is the doorknob. So it opens this way. Where would you push on that door to exert the most torque? Well, you'd push on the door handle right here, right? I'd push like that. And that increases the value of R about that rotation point, and so that I don't have need as much force. Also, if you push right here close to the hinge, it's really difficult to open that door because you've decreased the value of R. You could also notice right here that the angle between R and theta is 90 degrees. R and F is 90 degrees, and the sine of 90 is 1. So that's really good. If I push on the door handle like that, I'm going to decrease the torque because I'm not pushing at the best angle. I'm not pushing at a perpendicular angle. Now, finally, there is one kind of useful definition of torque, and then I'm going to show you another demo, and then we'll talk about equilibrium. Like I said, there's not a whole bunch in this chapter. It's really this. What is torque? And I like to put this O because it's important to remind ourselves that we're calculating the torque about a particular point. We can write torque as F perpendicular R. So imagine that I have this situation again. There's my point O. Here's my force F. I can, instead of calculating the angle between those, I can calculate the perpendicular component of F, and it looks like that. It's the value of F that's perpendicular to R. And you'll notice that this technically is the same as F sine theta. So F sine theta is F perpendicular. Now you could also write this as this, F R perpendicular. So now I'm going to take this and draw it as a line and find that is my R perpendicular. That's my distance from the point to the line of the force, but it's perpendicular. And that also is R sine theta. So you can group the sine theta with the R and you get R perpendicular. You can use the sine theta with the F and you get F perpendicular. They're all the same thing. They're all the same. Okay, so this is a really big deal. Now I want to use this to show you the center of mass. And let me show you a demo, and then I'll show you the center of mass. Okay, because I'm going to show you how to find the center of mass with a stick. This is a meter stick. Okay, and I'm going to put, it's got chalk on it, I'm sorry. I'm going to put my hand, one hand right here at 80 and one hand right here at 40. Now, you know the center of mass is right here at 50 at the center point. Okay, we already know that, and I'm going to show you why that's true. Now, if I slide my hands together, which one's going to get to the center of mass first? This is a trick that you should do because it's awesome and you can show it to your friends. I'll show you another trick. Oh, I need another person to do that. Well, we'll see. Okay, so here I'm going to slide these together. They meet at the center at the same time. And that's kind of awesome. It doesn't even have to be uniform density. I mean, you can have the center mass somewhere else. I can add an extra mass to there, and they still meet at the same time. So how do we find that center mass? Why is the center mass where it is? I'll get to that in a second, but I want to show you this trick since we're talking about it. So why do your two hands meet at the center at the same time? So here's the stick. And then here's one finger, there's a center mass, and there's another finger. The center of mass is the location at which we can apply a single gravitational force on the object. So gravity pulls on all parts of the meter stick. But if I place that as a single force at the center of mass, then I get the same torque equation. So it's a cheat, right? Because I don't want to deal with all those masses in the meter stick. So here I have this mg, I have the weight of the stick pushing down. I have this finger pushing up, I'll call that N1, and then this finger pushing up N2. So I know that it's in equilibrium, so that the net force is 0. But in this case, actually, I don't really care about the x direction because there's not that much right there. So F net in the x direction, in the y direction, is going to be N1 plus N2 minus mg equals 0. But that's not that useful. Okay. What is also true is that the net torque has to be 0. So in order for the net torque to be 0, the one that is closer to the center of mass is going to have to exert a greater force. So let me show you how that is. Let's pick this as my torque point. If I pick that as my torque point, then there's no torque done by gravity. That's kind of nice. So here I have R2, and here I have R1. So torque about that point, the net torque, is equal to 0 because it's in equilibrium. So the torque due to this finger is going to be equal to counterclockwise, right? It would make it want to rotate this way, which is counterclockwise, so it's positive, into R2, and then the torque from this one's going to be making it rotate that way, so it'd be negative, minus that's a 2, N1 R1 equals 0. Now, just conceptually, if R2 is less than R1, then N2 is going to have to be greater than that because these two have to be equal to each other. So that's the point. When we're going to do problems like this, okay, N1, in this case, it's further away. It's going to be smaller than N2. Now, remember that the frictional force for sliding friction is the coefficient of kinetic friction times the normal force. So the finger that has less normal force is going to have less friction. And so if I push my hands together, they're not both going to slide. The one with less friction is going to slide. So what happens is that when I push, the one that's further away from the center mass has less normal force because of torque, and therefore less friction, so it's going to slide. This one's going to stay still. Until this one gets closer, then this one slides. So they're going to end up at the center mass all the time, and that's kind of awesome. Not all the time. If it's not a uniform surface, if you have different coefficients of friction, it doesn't work. Okay, let's find the center of mass. Define the center of mass, because this is kind of useful. Imagine that I have, dropping my meter stick, I have 3 masses, and they're at different locations. Here's M1, here's M2, here's M3. And they're on the x-axis, so this has an x value of x1, x2, x3. My chalk's not working so well. What if I want to calculate I want to balance, these are rigid, they're connected by massless rods, and I want to push somewhere with a force F so that it's in equilibrium. Well, I know that I have these forces down here, M1G, I have this M2G, I have this one, M3G. So the net force in the y direction, F net, is going to be equal to F minus M1G minus M2G minus M3G equals 0. That has to be true. Okay. So I can write this as F equals G times M1 plus M2 plus M3. That has to be true in order for the net force to be 0. Now, the net torque has to also be 0. So let's pick this as our point, origin point right there, O. And I'm going to erase this. Let's put up here. F equals M1 plus M2 plus M3G. Now I can erase all this other stuff. I'm not very good with space right now. So I want to calculate the torque about point O. Torque net O. Okay, so I have 4 forces, and the torques have to add up to 0. So let's start this right here. This is going to be a force that would want to make it rotate this way, which is clockwise. So that's going to be negative. Negative the force, m1g, times its distance, which is x1. Then I have this force, which I don't know where it is, but I'm going to call that xc for the center of mass. Okay, and so that's going to be a positive torque plus F xc. And then the sun came out. Look at that. And then I have this one minus m2g x2 minus m3g x3. And that has to be equal to 0. Let's solve for xc. So I'm gonna add all those negative terms to the other side. I get f xc equals m1g x1 plus m2g x2 plus m3g x3. Now remember f is that. So I'm just going to put that in there. m1 plus m2 plus m3 times g. Now, the first thing, the g's is in every single term. So cancel, 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 cancel. The center of mass, the center of gravity, does not depend on g. It's kind of interesting, right? Okay. Now I divide both sides by this, and I get x center of mass is m1 x1 plus m2 x2 plus m3 x3 over m1 plus m2 plus m3. And that's how we define the center of mass. If you've done weighted grades, this is a weighted grade. Test grades, quiz grades, final exam grades, they all have different weightings divided by the total weighting. Okay. We can write this more generically as x center of mass because it can be any number of pieces. I could have more than 3. I could do this for 20 pieces. X center of mass is equal to the sum over I, mi, xi, over the sum over I, mi. So this is just 1, 2, 1, 2, 2, 3, 3, and we're going to add them all up. That's exactly what we did right here. But you can do the same thing for as many as you want. Now, you could also do this in the y direction, because imagine if I move, what would happen if I move this mass up here, just straight up? Well, none of my calculations would change, because I could use r perpendicular for this force, which is still x1. So it didn't change my x center mass. But now I'd have to do the same thing for the y center mass, because I don't want the, I'd have to push in a way, well, and if I want to balance it, I wouldn't have to. But if I wanted to push in another way, I could find the y center mass. Okay, so that's center mass. I want to talk about one more thing. And I wouldn't really put this in here, but they did. Simple machines. You know, everyone loves simple machines in middle school because they were pretty cool, but it is an example of torque. So let's think about a lever with a pivot point right there. If I push down with some force Fi, I'm going to use a scalar version. It's going to push up with some force Fo. And this, they call this Li for the input length and Lo for the output length. The torque has to be equal, so Fi Li is going to be equal to a positive minus the negative of that, but I'm just going to put it equal to Fo Lo. So we can solve for the output force. Is this how they do this? Well, that's it. This is your simple machine equation. That's fine. So what this says is that I can apply a smaller input force and get a larger output force. And that's what simple machines do. But you don't get forces for free. It's not free. You do pay for that, right? And you pay for that in terms of the work. Because if I have a large lever arm here and I push with a smaller force, I get a larger force out, and that's great. But I'm going to have to move if I move down like that, notice that this distance that I apply that larger force over is much larger than the distance of the force that I get out. So in fact, the work over here, F times delta X, is equal to the work over there. So simple machines don't give you energy. They trade. You're trading using a smaller force over a larger distance to get a larger force over a smaller distance. And then there's pulleys and things like that too, which are awesome, but I don't really want to get into that because it's not super important, I don't think. I think torque is important. And so let me put down the final thing here, the most important thing, just as a review. So we have the definition of torque about some point is Fr sine theta. And this does have units of Newton meters. And then we have our new conditions for equilibrium, F net equals 0. And torque net about some point O is equal to 0. This is actually two equations because that's the vector. This is just one because it's a scalar. Technically, it's a vector too. And then we have the definition of the center mass. Xc is the sum over I, mi, xi over the sum of the mass. And if you have an infinite uniform distribution of masses, this sum becomes an infinite sum of infinitely tiny pieces, and it becomes an integral, but you probably don't need to know that. So that's all there is for that chapter 9. The problems are awesome, though. And I told you I would tell you how this Tensegrity works. I'm going to do that because I don't want to lie. So going back to this. So this works because the top piece is in equilibrium. So what forces are acting on the top piece? Where there's the downward gravitational force that acts at the center mass, wherever that is. And I know where it is, but it doesn't really matter. Right here, I have this string pulling up on the top piece, right? Because the top piece has this bottom little hook down here. So that's actually pulling up. And that's enough. Just that string is enough to make this be in equilibrium if the string was pulling up exactly in the same position as the center of mass. It wouldn't be very stable, but it would be balanced. So instead what we do is we shift the center mass. The center mass is over here. So this string by itself would make the whole thing rotate about the center mass. And so what we do to fix that is to have these other two strings right here to pull down. So there's net force is pulling up on it. And then we have the downward gravitational force and these two tensions pulling down on it to make it in rotational equilibrium. And so that's kind of cool. So you can build anything like this. It's super easy. You just need to have a hook below that and then something over here to hold it up to. And again, I'm gonna have this as a physics problem that we'll solve later. Okay, so that's it. Hopefully you find that useful. The end. There we go, thumbs up.